Hi, welcome to Fundamentals Friday. Today we're going to take a look at a rather unusual and often little known aspect of ceramic capacitors. In fact, it's a really undesirable aspect and a real trap for young and old players alike if you're not aware of it. So let's have a look at some basics first, and then we'll jump over to the bench and I'll show you. So I won't tell you what it is yet. I'll let you figure it out on your own. But a capacitor. Right, simple RC charge circuit like this, very common application for capacitors. RC, time constant, charges up, gets to a certain threshold and you can detect that and you can use them as timers. Very typical application, not that accurate because, as we're aware, capacitors are not particularly high tolerance devices. And if we take a look at some typical ceramic capacitors, we're only talking about ceramic capacitors here, then they're basically divided into several classes. Class 1 capacitors are your NPO and your COG type, and a couple of more obscure ones that you've probably heard of, and as you might know, they are actually very stable capacitances with temperature. Okay, so once you've actually measured them, then they stay pretty stable. They basically do not change with temperature. So they're typically your low values. You know, your 1 nanofarads and under you can get in these NPO COG types, but your larger capacitance values, you know, your hundreds of nanofarads, your microfarads, or your modern ones, you know, you can get like hundreds of microfarads now in little surface mount ceramic packages. The technology is absolutely incredible. Anyway, I won't go into a huge amount of detail, but basically you've heard of these codes before. Things like X7R, for example. What does that mean? Well, there's a 3-letter code like this. It's part of the EIA code system, and X, for example, the first letter represents the low temperature, so minus 55, and the next digit here represents what the high temperature limit is. In the case of X7R, it'd be minus 55 to plus 125 degrees Celsius, and the R part is the tolerance of the capacitor. In this case, X7R plus minus 15%. Pretty basic stuff. Or an X5R, for example, is basically the same capacitor but with a slightly lower, higher temperature range. And you're familiar with these things, and as you might know, if you're an experienced designer, picking something like an X7R is a relatively stable high value capacitor to use, a relatively stable dielectric. So you might use, say, an X7R or an X5R in an RC time constant like this, but wait until we get to the bench. I'll show you a trap. It's not just about the tolerance here. Now, if we look at the RC circuit, which I'll use in the example on the bench in a minute, you're familiar with the charging graph, charging response of a capacitor, and time constants. One time constant, or TOR as it's known, is the simple formula R times C. And you know, a basic building block circuit, basic building block formula you should be familiar with. And one time constant is the point. Here it is. One time constant is on the x-axis here, and the percent of charge is on the y-axis here. And if we put a step voltage in like this, then our capacitor will charge up with a exponential formula. The main formula is actually down here, but you can simplify it. We won't go into details on that. We'll just use our simple R times C formula today, and we'll be measuring this one time constant period. One time constant is where the voltage charges up to roughly 63.2% of the final voltage. Why that particular number? Well, it has to do with the fact that when you plug 1 e to the power of minus 1 up here, that's the number that actually spits out of the formula, and it's useful. And basically a capacitor is essentially fully charged, you could say, after roughly 5 time constants, or 5 times RC. A capacitor is fully charged. So if you know your resistance, you know your capacitance, you can figure out how long it takes to fully charge that cap or get to 1 time constant. Pretty simple, pretty basic. And of course there's more to this as well. There's a class 3 down here using yet more exotic materials and yet more unstable materials, again for ceramic capacitors. So pretty much class 1 is the most stable. Class 2, they're okay, but as we'll see, there's some few traps in there, and well, class 3 is even worse. So let's not go there. What we'll take a look at today is an X5R or X7R capacitor on the bench, and we won't be taking frequency into account as well. It'll be nothing to do with that. It'll just be the capacitance, this tolerance figure here. So if we have a look at, say, the X5R capacitor we're going to go look at on the bench now, it should measure plus minus 15%. Does it? Well, yes, and maybe no. Come with me. Okay, the first example we're going to look at is a typical 0805 Class 2 ceramic capacitor from Murata, one of the top manufacturers. And here's the full part number. Got this from Farnell's, and it's a multi-layer ceramic capacitor. X5R, basically the same as X7R, it's just slightly lower temperature. Nominal 10 microfarads and 6.3 volt rated. So one of these, low voltage rating ones, you typically only use them on 5 volts or 3.3 volt rails or something like that. Now, it's a nominal 10 microfarads with a tolerance defined by this letter here. In this case, it is K, and I'll show you the data sheet in a second. That is plus minus 10%. Now, that's not the X7R. The X7R value of plus minus, or X5R value of plus minus 15% we saw before, that's its temperature, or it changed the temperature coefficient over that full temperature range. So, but this is the initial tolerance as you'll measure it and buy it from Murata straight out of the packet here. So there you go, you have to decode these rather complicated part numbers for these things, and you'll notice that the 102 is the value there, 10 microfarads, and we've got K, number 8. So we have to drop down to number 8 and see what that is. And here you go, here's the full table available from Murata, and K, there it is, plus minus 10%. So, assuming that we measure it under the defined measurement conditions for this capacitor, then we should measure 10 microfarads plus minus 10%. Okay, now what frequency are we supposed to measure this at? What do the specs define it as? Well, here it is, capacitance, if it's greater than 10 microfarads, there it is, at 0.1 kilohertz, 100 hertz. There you go, at a 1 volt test voltage plus minus 0.2 volts RMS. So, well, let's use our LCR meter. Here it is. I've surface mount soldered one of the capacitors onto this little adapter board so we can plug it into our breadboard. No, it's completely cooled down from the temperature change. It's at room temperature. We're like 23 degrees C here in the lab, so the temperature is not going to change during this measurement. And 100 hertz, here we go. Look, we're practically bang on to our 10 microfarads value. Okay, let's round that to 10 microfarads, okay? This is spot on. Okay, so let's mount that on our breadboard here. We've got our bang on 10 microfarad capacitor there. We've got a 1K resistor in series with that, so we've got that RC circuit I showed you on the board before, so we should be able to see the charge of the capacitor there. And I've got that hooked up to my function gen here, and I've got it output in a square wave, so we get a nice big step change from 0 to 5 volts. Remember, this is a 6.3 rated cap, so we're safely under that. 5 hertz repetition rate with a 20%, 5 hertz frequency with a 20% duty cycle, so that'll allow us to see the charge and discharge cycle of the capacitor. And here we go. If we look at our scope here, let's single shot capture that. Bingo! There is the charging of our capacitor. Now, there's our green step change on the input there, and we're charging up until we get to 100%, and we're basically then dropping it back down, and we don't care about the discharge period here. We're only going to be looking at the charging period, so it's got enough time to charge up. So there it is. There's our beautiful charging waveform. Now from this, we should be able to turn on our cursors, measure one time constant here, and from that one time constant equals R times C, we should be able to verify that that capacitance is correct. So if we go into our, select our cursors here, let's go the Y right down the bottom, like that, Y2, let's take that. What we want, because we've got a 5 volt signal here, we basically want that to be 63.2% of 5 volts. So that is 3.16 volts. So we set our cursor, our delta Y, to 3.16 volts. We'll get close enough, okay? just in the ball, 3.162. There we go. So that's the delta difference between there. So that height is 63.2% or 1 time constant. Now we go into our x here, and we want our x right at the start period there, and x2 cursor right where that intercepts the waveform. That's pretty close to spot on there, and we're getting 10.6 milliseconds as the difference there. Let's plug that into the formula. Alright, so what do we have here? We measured precisely, basically we rounded it to precisely 10 microfarads. Torr equals R times C. We measured that time constant to be 10.6 milliseconds equals 1K times C. We're trying to calculate C. Rearrange the formula. 10.6 milliseconds over 1K equals 10.6 microfarads. Hey, that's not bad. That's pretty close. We're only 6% out there, still within inside that 10% value that we, the data sheet value. Yeah, it's a little bit off. It is 6% to what our really accurate Agilent LCR meter told us. But hey, you could put that down to the error in the cursors and, things like that, eyeballing this sort of stuff. So, we're going to call that near enough. Not a problem. Okay, do it one more time for 0 to 6 volts, and I've done the cursors here, and we're basically getting 10.1 milliseconds, or translates directly into 10.1 microfarads. Everything's hunky-dory. But what happens if we change this voltage and we add a DC bias voltage in here? So our low level is our waveform is going from 0 to 6 volts. As you can see, here's our ground reference level here, DC coupled inputs, and 1, 2, 3, 4, 5, 6. So we're getting 6 divisions there. What happens if we actually set this thing so our low level here is, say, 5 volts? So it's going between 5 and 6 volts. So the capacitor always has a constant bias voltage of 5 volts on it. Let's have a look what happens. So if we do our single shot capture there we go. There's our ground level down there. It's still exactly the same as was before. 1, 2, 3, 4, 5 volts. But now our waveform is now superimposed, biased 5 volts up. But hey, that should not affect our formula at all. The time constant doesn't matter about what the initial value is. It's all about that step change. It makes no difference. Trust me, the formula ain't wrong. It's been around forever, and you can rely upon it. It's 100% correct. So let's go in and measure that, shall we? So let's take that up a little bit more, shall we? And let's bring that right down to here, say. Bring that waveform down to here, and then we can capture that again, and bingo, we can go in there and measure that. I'll even bring out the horizontal a bit so we can get a reasonable amount of accuracy in there. Once again, we go in there and we use our cursors. Now we've got to set, let's set our Y1 minimum, our baseline here, right down the bottom. No problem. Y2, let's go up because it's a 1 volt change. We're looking for 63.2 delta here, difference. 63.25, there we go, excellent. So that's fine. And we're going to X1 over here. X1's already set. It's that cursor over there. So we won't muck around with that. X2. Bring that over to the point where that waveform crosses there. What do we get? A delta, a time constant, times difference there. Once again, we're still getting to that 63.2% one time period. But look at this, 4.82 milliseconds. You whack that back into the formula, you get 4.82 microfarads. Our capacitance has halved. So if we go back to our full formula here for the charging curve of a capacitor, we'll actually just change it slightly. V0 here is actually V origin. It's the start of where the voltage starts at. Okay, so it doesn't necessarily have to be 0 like we saw in this case. It's starting from 5 volts and going up to 6 volts. The formula still holds. I mean, you read that in any textbook and it is not wrong. Okay, it is absolutely spot on. And of course, Torr is RC. And Well, so what is varying? Okay, our start voltage is staying the same. We've measured it with our oscilloscope. There it is. We're going up to the 6 volts, and we were measuring the time constant. We were measuring the time period correctly. That's 63.5% of the total change. Now our resistor in here are, well, a resistor is probably the world's most basic component. These things don't change. Okay, so it's a fixed known 1K. So what is left? What must be changing? Because we've measured all the voltages, we've confirmed them with the oscilloscope. Well, you guessed it, C. The capacitance is changing. It has changed. So it's dropped from that value we had before of 10.6 microfarads. It's dropped down to 4.82 microfarads with that 1 volt range, with that 5 volt offset. And it's got nothing to do with the 1 volt range instead of 5 volts. We can confirm that. Again, let's go back, remove the DC bias, and check that 1 volt range. It's not the range of the voltage, it is the DC bias which is causing this capacitance to drop. And here we go, just to confirm, I've set it back to 0 to 1 volt there, and there it is. There's our 0 to 1 volt waveform, and what do we get? So it's exactly the same amplitude as before, and we get, look, bang on, 10 milliseconds. Wow! Bet you didn't know that. These class 2 ceramic capacitors change their capacitance based on the applied DC bias level. Unbelievable. Who knew? They don't tell you that in the data sheets, the bastards. But not only that, the capacitance also changes with the applied DC voltage level as well, not just a DC bias offset. So the AC level as well. In fact, the capacitance can go up, not decrease, as we've seen with an applied AC voltage, depending on the level, depending on the construction technology and the dielectric used in a particular type of capacitance. And it can even change fairly drastically between the same family with different size capacitors. Unbelievable. So the same family, the same type, the same XR7 rating, or whatever it is, it can change. Man, hate capacitors. So are you shocked? Well, you should be. Now let's go on to a different type here. This is a pretty horrible Y5V ceramic cap, minus 20% plus 80% initial tolerance, 10 microfarads, 16 volts. And let's measure it and see what we get. So I measured a value on the LCR meter of 8.65 microfarads. So let's see what we get on the scope. I won't bore you with the operational details, so here you go, 7.8 microfarads, 7.8 milliseconds, exactly the same resistor, everything else. So it's a reading quite significantly lower than that 8.6 we were getting before. And, well, that's not a mistake. As we've seen, capacitors can vary with bias voltage and also other things like just the basic applied voltage. Now let's check this same Y5V capacitor from 0 to 10 volts instead of 0 to 1 volts. Once again, there's no DC bias here at all. What do we get? Wow, look at it. It looks substantially different. And there we go. Look at that, 4.6 milliseconds. Goodness, our capacitance once again has like halved. Pretty horrid, but look at this. The wave shape, the charging waveform has actually changed. It is not that sort of, rapid rise and then the decay like that. It sort of goes up like this and then decays. Totally different to what we saw before. So these Y5V caps are absolutely horrible, and there's some weird physics going on here based on the dielectric and the construction of these Y5V capacitors. They're nothing like those X7Rs that we got before, or even like this same Y5V but down at 1 volt. All we've done is now change it to 10 volts. There we go, we're 2 volts per division, and like the characteristic of the charging of this thing has changed. Oh man, you definitely don't want to use these for any sort of timing application. And what happens if we add a bias level? We'll add a 9 volt DC bias level. Remember, this is a 16 volt cap. This cap will only go up to 10 volts maximum output voltage on a square wave. So we're going from 9 to 10. So we're going back to that 1 volt difference, that 1 volt change. But let's have a look at the waveform. And this is what we get. Now, yes, we're back to that characteristic shape that we saw at 1 volt, that proper, the curve you actually expect for the charging of a capacitor. But look, what we're at, 1.5 milliseconds, 1.5 microfarads. It's dropped by, not quite an order of magnitude, but geez, it's getting there. And this is for a 16 volt rated, Wi-Fi V cap. And that we measured the value, measured the capacitance of with our good LCR meter. It's hopeless. Now, the real problem with all this is that this is rarely mentioned in data sheets. There are exceptions to this. Some manufacturers do actually remind you of it every now and then, but hey, sometimes it's almost next to impossible to find for your particular manufacturer. Now, this particular Murata capacitor we're actually using here, we used first of all the 0805 here, the 6.3 volts, 10 microfarads. There it is there. And if you jump on over to the product page here, by the way, it's not in the data sheet. You have to actually go to the manufacturer's product page for that specific capacitor. And here, look at this. Look at this graph right here. Maybe I could zoom into that perhaps. Not that great, but here it is. The capacitance. Oh, no, here it is. The DC bias characteristics of the capacitor. Look, 0 is like, this is the change in capacitance, i.e. the drop in capacitance with the DC bias level. And that's exactly what we saw here. And look at that graph. It can drop as much as 60% by the time it gets to 6.3 volts. So it's 6.3 volt rating. It's dropped by a massive 60. The capacitance has dropped by 60%. It's unbelievable. And look over on this side here. Here are the AC voltage characteristics I was telling you about. I don't have time to set up experiments to verify this one today. I want to keep it a bit short, well, as short as possible. Probably been going long enough already. Anyway, the capacitance change with AC voltage RMS. Look, quite significant, up to like plus 15%, minus 30%, right down at low signal levels. Unbelievable. Who knew this stuff? Right, and AVX are quite decent. They actually remind you of it. Here it is. Capacitance change versus bias voltage. Look at the drastic drop-off in this particular one. I mean, this is just awful. Look at this. This is for one of their general purpose multi-layer ceramic capacitors. So it actually goes up a bit. As I said, it can actually go up at small DC bias levels, and then it drastically drops down to, once again, these are high voltage caps, but it can drop way, way off 80, even 90% or more of your nominal rated capacitance just by adding DC bias or by changing that AC voltage. And anyway, you can get some interesting little obscure articles here which tell you all about the physics and stuff like that behind all how all this sort of stuff works and how the various crystalline structures work. And look, did you know that the crystalline structure changes with temperature? Look at that. This is for a certain type of dielectric and construction, which is found in typical class 2 and class 3 multi-layer ceramic capacitors. So depending on the temperature, it actually changes the crystalline structure. And then the DC bias, it goes in to try and explain the physics of how that actually works and how the DC bias affects the actual capacitance. So anyway, I'll link in this stuff down below. Check it out. And there's a lot more to it. Some manufacturers don't even mention it. But wow, it can be a real trap. Capacitance ain't capacitance. And here's an example of AVX actually showing you the effects of voltage. In this case, it's the AC voltage capacitance change versus AC voltage as well. And you can see how the capacitance can actually increase drastically, 50-odd% or so, depending on the AC voltage applied to it for these multi-layer ceramic capacitors. So yeah, really tricky business. Now, a couple of the manufacturers, namely Murata and AVX, these are the two of the better manufacturers in this field for analyzing and trying to correct. They're always improving their manufacturing processes and stuff like that for to try and eliminate this kind of effect, although it's next to impossible with the class 2 capacitors. But at least they're aware of it, and they do allow you tools to actually simulate it as well. The the Murata website has a tool called Sim Surfing, and it allows you to actually plot this stuff with bias values and all that sort of stuff. And AVR as well, they have SpyCap software, which will do a similar thing as well. So you can play around with these simulation tools, but there's nothing better than actually whacking it on your bench and seeing it for real like we did today. And I won't bore you with the details, I'll leave it up to you to experiment with this, but if you drop that DC bias level, like say 1 volt at a time, so if you went from 9 to 10, and then 8 to 9, and 7 to 8, and 6 to 7, and so forth, and dropped it down, or increased it, then if you plotted that and measured your capacitance at each value, you would get that similar characteristic, huge big characteristic drop in capacitance versus your bias voltage, exactly like the manufacturers tell you, if you can find their data. So there you go, that's an interesting fact that not a lot of even experienced design engineers know about, because, well, they just throw their capacitor in, they assume it works, yeah, they know about all sorts of other characteristics of the ceramic caps and all your temperature coefficients, and mainly all they care about is temperature, but what a lot of people don't think about is that capacitance can change with voltage as well. Not only DC bias voltage that can have a drastic effect, but also the applied AC voltage as well. So it's not just like RC time constants like this. Of course, if you're using the same circuit for, you know, you're doing filtering and things like that, it can really matter based on the signal level. It can be really quite critical. So you have to be very careful with how you use these modern ceramic capacitors. They're fantastic with all this wonderful materials technology that goes in them to give you incredibly high capacitance in incredibly small volumes for SMD and stuff like that. But yeah, there's a few downsides, and it's not just temperature, voltage as well. Trap for young and old players alike, certainly. Now, this only applies to class 2 and above ceramic capacitors. It does not apply to electrolytic capacitors, tantalums, and class 1 NPOs and things like that. So, yeah, and there's, of course, I've done videos on other traps with these ceramic capacitors as well. Piezoelectric effect, of course. Well, I'll link that in down below if you haven't seen that video. So there's lots of stuff to think about here. Man, so many traps. Got to be careful. Electronics design ain't as easy as it seems on the surface. You dig deeper and deeper and deeper, and, well, if you're in a critical application, this can be a really big deal. So there you go. Hope you enjoyed that video. There's so much I can do on this subject. I can measure, you know, hey, let's not even get into frequency changes and all sorts of other stuff thrown into the mix. Oh, goodness. Could do hours and hours of videos experimenting with this sort of stuff. But you should get to the bench and have a play around with it yourself. It can be rather fascinating. So there you go. Hope you enjoyed that one. If you want to discuss it, jump on over to the EEVblog forum. Link is down below. If you like Fundamentals Friday, please give it a big thumbs up, even though, well, it's actually Saturday. I'm shooting this on. Yeah, I'm a bit late. Anyway, catch you next time.